Welcome to class 21 in thermodynamics. We're going to talk about entropy from the Gibbs equations, which is another name for some of the equations we've already been using or looking at, I should say, on the cheat sheet. So let's flip on over to here. We're going to do some first principle stuff. And so right here, let's go ahead and find these on a per mass basis right here. So these are the Gibbs equations, I think we could call them. Yeah, sure. On the per mass basis, let's figure out how we got there. So first off, we're going to take the conservation of energy right here. So in infinitesimal form, usually I'm used to actually writing this, or I prefer, for consistency, to write U2 minus U1 is equal to Q1 to 2 minus work 1 to 2, right? So there's a basic equation, but now you could say, well, if we take differential form, we're at du is equal to del Q minus del W, and then just rearranging right there, so you'll see that we get the same thing. So first, let's go ahead and take this known thing. Remember that we had, well, as a definition of entropy, right? We had the integral del Q over T, right? So we're just flipping this thing around right here. And we're saying, okay, we'll make that a differential instead of integrating. And I did not make that we're not talking about a cycle right here. We're just talking about the definition of this right here. We also have the definition of work. So we can replace with these two things back up into this equation right here. And what we have is T, D, T, that's going to be a bigger D, sorry, ds is equal to du plus P, D, and this capital V, right? So we're not talking about a small v. And then, of course, we could just go ahead and make them into, on a per mass basis, divide mass through, and you go to a little s, a little u, and a little cursive v for the specific volume right there. And although this is kind of derived, right, so this needs to be a reversible process for this to actually be true right here, and we're deriving it by assuming this right here a reversible process. We do know that because once we take care of the reversible process, that we can now have just state functions, like we end up getting from one spot to another. So we're totally okay right here. We have to be careful about what our path is, but this right here derivation is totally fine to get between to get at a state. Right, the book says, although derived using reversible process assumption, this can be used for irreversible state-to-state property calculations, but maybe not the path, right? But here's like the first Gibbs equation, but we're going to wait until we summarize at the end. So another approach to putting this thing together, or putting on the other Gibbs equation, is to look at the definition of enthalpy, which is going to be capital H is equal to capital U plus PV, right? So this is internal energy, and this is like, we can think of this as flow work, right? P times V. So we can take this in a differential form, just take the derivative of it right here. And then, and of course, both of these can change, so we need to do the product rule. I think, is that the right? Yeah, I'm using the right phrase, product rule. And go and then rewrite this thing out for du, and so we have dh, and then we have minus p dv, and then minus v dp, right? So these are the volumes right here. But then we can see if I'm trying to. Okay, yes, okay. So we can replace the du that we might get from up above, right, in here. Substitute this and into up here. Right, so let's see if we can get that thing to, there you go, refocus. And so what we're going to get is T ds is equal to dH minus P dV minus V dP plus P dV, right? And so you can see that those two are going to cancel out from each other. So what we're left with is a T ds is equal to dH minus V dP. Right, so here's our second Gibbs equations, and then if we go ahead and divide through by mass, we end up with T ds is equal to du plus P dV, and T ds is equal to dH minus V dP. All right, so these two things are our Gibbs equations in the per mass version of the thing. Two forms of the Gibbs equations. So what do we use them with? Well, we're going to see that in the next section. All right, so first I'm going to finish off with, so not in the next section, this was in 6.4. We're going to take a quick look at 6.5, which is sort of a little detour. I kind of think maybe I should flop these things around, but this is the order in which I have the notes. So we're going to go ahead and continue with this. We're going to talk about this. We'll talk about the entropy change of a solid or a liquid. So this is a little bit different. I mean, we're using this equation right here, which we just went ahead and put together. But we're going to expand upon this after we've done an example with this. Okay, so that was a whole bunch of directing traffic. So let's get into here because I have more time. I'm at the 7-minute mark, and this won't take very long. And then I'll do an example that's associated with this portion right here. And then we're going to do a deeper dive into this section after that example, right? So let's talk about the entropy change for a solid or a liquid. First thing that we should note is that in this equation right here, the change in volume is very, very small, right? You know, it's so I guess it'll go very, 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 very small for a liquid or a solid, right? So the change in volume doesn't amount to a lot of much. In fact, we assume basically they're incompressible, that meaning the volume can't change. So we can go ahead and just ignore that term right here. And then we also note that if we had specific, okay, so if the volume is constant right here, we can also, if you'll recall, that we had a definition of internal energy was CV, a constant volume specific heat, times dT, right there. And quite often for solids and liquids, we will just not even bother with the V in there. We'll just say that's called the specific heat for the thing, because it's what we use most often is for constant right there. So what we can essentially now do here is, I guess I'll rewrite it, right? We can say that T ds is equal to CV dt, or as you see right here, ds is equal to du dt. As I wrote up there, I guess I'm just rewriting the thing up as C, and I'll call it V over T dt. And then it makes sense if you integrate both things that we could have the S2 minus S1 is going to be CV times the natural log of T2 over T1. So this right here, of course, is limited to this case of having a solid or a liquid right there. So let's take a look at an example in the next video. So let's see, what we call this, we will introduce entropy and the Gibbs equations is what this video will be called. And then we'll do an example with, is it solid or is it liquid? I can't remember. We're going to do liquid water, right? And we're going to compare it to using a constant specific heat and compare it to what's in a steam table I believe so. I think that's what we're going to do. So let's just check that out.